And I've introduced some new notation, and the notation is that if this is a cell, I'm calling tau the internal coordinate of the charges inside the cell. So, for example, this is the internal coordinate of the Viney center, and that's the internal coordinate of the ion. Okay? So if you plug these expressions there, the j's cancel. So the thing you're summing over is independent of j, and you have nb of those, and that cancels the nb there. So we get a very simple result. Okay. So in other words, I'm drawing here again just a crystal cell. What I'm calling P bulk is really just the dipole divided by the length of these 2-point charges, one real, the other fictitious. Right? So just this. So, are we getting anywhere? Let's see. We'll see that we're getting somewhere when we look at the other terms. And that's where the reason for all these trivial manipulations will become crystal clear, because something interesting will hit us in the face. Let's, for example, now compute the contribution to that P chain from the charges that are in the head region. Okay? And now remember the other thing I said about my construction. When the chain becomes very large, the head and the tail regions are non-extensive. So this is just the interior that is growing, growing, growing. So for the purpose of that formula, we can basically replace, the fact that these charges are not exactly at the same place is negligible, because their separation, when you divide by L, is negligible. So we can basically, in that formula, pretend that all of them are sitting at the same point, which you can take to be this point. Okay? So I'm writing an approximate sign in the sense that it becomes exact when we take L to infinity. And so now I just add algebraically the number of positive charges, so the number of ions in that region, and I subtract or add with a negative charge the number of Viney centers that I've assigned to that region. So what I've done here, if you compare with the equation on the board, I've just replaced all the x's by the same number, which is the location of the head in my coordinate system. And let me do the same thing for the tail. So if the head is at x0, if the head is at this cut, I'll put the tail at that other cut. Okay? And now I will use a very simple fact, which is the chain as a whole is neutral. Otherwise, the polarization is really not well defined, it's origin dependent. So we're talking about a neutral system. And obviously, the bulk is neutral by construction. So that means that whatever charge is in the head region, there is an equal and opposite charge in the tail region. Right? So, using charge neutrality, I can write this just by putting a minus sign in there. Okay, so now I just add these two contributions. I'll call that the surface contribution, the net contribution to the polarization from the two surfaces or the two ends of the chain. And the x zeros cancel. Right. So and I just get a contribution from this guy here. We're almost there, just a tiny more step, which is, remember that in the thermodynamic limit, the difference between the length of the chain and the length of the bulk region is negligible. So this is, in that limit, is just 1. Okay? So, lo and behold, what have we found? We have found that the polarization of the chain So what is special about this quantity? It's an integer. And just counting, right? So we've actually arrived at a very deep result. We can take the thermodynamic limit and we get that the polarization of the chain is given by this expression here, which we can calculate in a cell in the bulk region. And we get the right result, except possibly for an integer multiple of E. Okay? So in other words, polarization is a bulk quantity modulo E. So this argument solves all those lengthy discussions a long time ago, and it proves that the polarization is a bulk quantity, but in a funny sense. Most quantities are purely bulk quantities, modulo nothing. This one is almost a bulk quantity if you're willing to live with the uncertainty of a quantum, of an integer charge in one dimension. And you can see that there is topology hiding here. Whenever you have integers, you can guess that there is topology. I just want to make a few comments. So, any questions? Right. Right, and if you think about the thermodynamic limit, the prescription is that when the chain grows, it's really the bulk that is growing, and this remains small. So in that limit, this just basically, on the scale of the chain, shrinks to a point. And I've assigned this coordinate to the head, and I've assigned that coordinate to the tail. So this argument is only exact in the thermodynamic limit, but that's the bulk limit. That's what we're after. So that's the point. So all these quantized effects that I'll discuss later, actually the quantization is only exact in the thermodynamic limit. So keep that in mind because it's actually important. Thank you. Okay. There are a few interesting things, comments that one can make about this. And sort of coming back to the very first thing that I said when I was going through possible definitions of polarization, like the charge density, the moment of the charge density in a cell, like you can find in textbooks that. So let me now go back to remembering that these are not really point charges, but they are centers of orbitals with a finite distribution. So let me make a cartoon of those orbitals. So I have one here. Maybe it looks like this. And I have another there, and then another there. Okay. So let me call this Wj equals -1, for example. This is W0. This is W1. So I have here a cell. So this is A. So they are separated by A, right, in the middle of the chain. So let's pay attention to this equation to understand what the bulk polarization is and what it isn't. Okay? It is not the dipole of the charge distribution in the cell. And I want you to understand that from this picture. If you compute the charge density from equation 3, the second equality, the density in the central cell, 0, has contributions from the tails of the Viney functions in the neighboring cells, right? So the Viney functions overlap in general. Okay? So this quantity has contributions not just from this Viney function here, but from the neighboring ones. Of course, in general, even from further ones, but that decays exponentially. But there is a finite overlap in general. Because what the polarization is from this formula, and now let me just focus on the electronic contribution. Is just the center of charge of this function here, only this one. Okay? So it's the integral over all space, because remember, it also spills to the other cell. So it's not an integral over a cell. You integrate in principle over all space. Of course, it's localized, so you don't have to go very far. So if you have to remember, from all this first part, one thing is that this is not that. And look at this picture. And this is the bulk polarization, the electronic part. Okay? So here, I mean all space. And so the deep message from here is that the polarization is a funny quantity that you cannot obtain from the charge density. You can obtain from the moment of the charge densities of the individual orbitals when you choose them to be your Viney functions. Okay? Okay. So, so the procedure, given a chain with a certain surface preparation like this one, the procedure to sort of decomposing the polarization of the chain into bulk and surface contributions is very simple. So you choose a bulk cell, you start somewhere in the middle, you tile it to the right, you stop at some point near the surface, and then you count the excess charge of the point charges that are left after you've tiled. So you only tile up to a region where you still haven't lost the perfect periodicity. And then you just count whatever is left, right? So that gives you that part. So the bulk part is just the dipole inside the cell of these fictitious charges, and the surface part is this. But of course, this procedure is not unique. I can choose a different cell, like this one. So now I've placed my cut here. That's my new x0 prime. And now I tile that. And then I can stop here, for example. And then if I count the charges that are left, I get a different number. But that change is exactly compensated by the internal dipole of the two cells, right? Because in one case, sorry, the drawing is a bit messy now, so focus on this blue square. In one case, the arrow pointed from the minus to the plus inside the blue square, so it points to the right. And in the other case, the bulk dipole now points from the minus to the plus inside the red square that points to the left. And I'll leave that as a simple exercise. You can check that, the change is exactly equal and opposite. And actually, it's an integer, right? Okay, I think that's clear. So, again, that's another way of seeing that the bulk polarization is only defined model E in one dimension. And that the other important message is that we should not think of this integer charge as any measurable real surface charge, so it's not unique. What is the real surface charge? You know, the thing that appears in P dot n equals sigma, so the bound charge, is really P. So it's the polarization of the chain. And that's not an integer. Okay? So, okay, so we've done a lot of formalism. I want to show you some results, and what I want to do. It doesn't. I will cover that later. But basically, when you choose a less localized set, if you just have one band and one Viney function, the center doesn't move. So it can change shape, but not center. Or it moves by an integer. And so that is sort of already accounted for by the fact that we accept that the bulk polarization is only defined modulus quantity. Yeah, right. Excuse me? Yeah, so there is no reason to choose any other set. In one dimension, what Tim was saying is that the construction is so trivial that there is no reason to choose any other. But one can ask the question, of course. And the answer is that the shape of the orbitals can change, but the center doesn't. When you have multiple bands, you have several Viney functions, and then the individual centers can change, but then the changes cancel when you sum over all the. Yeah. Yeah, I will come to that in a moment. Yeah, I'm trying to go very carefully. Maybe it's a bit tedious, but somehow I think that this problem is so simple that it's worth that to sort of see it carefully once, because then you sort of see all the topology appearing and the simplicity remains there. So I thought it was worth to go slowly just to, but I will get there. Yeah, so the polarization is equal to the macroscopic surface charge phenomenologically. So what we can say, and the reason I'm changing language is that I want to talk about surface charges now. And the way to read this equation is the following. For a given chain with a given surface termination, this guy is uniquely defined, and this guy is one that has the ambiguity. Okay? Okay, so how to compute the surface charge? So what I want to do in the numerics that I will show you is that I've sort of gone through an argument that this is true, but I like numerics and the proof of the pudding is to see it. So I want to compute independently this guy and this guy for a simple model and check that they do agree in the sense that we've been discussing. Okay, so we know how to compute this guy, right? Let's see if there are some more equations that I should have written. Yes. Yeah, so that's where we are. How do we compute the surface charge? So let me go back to my sort of pseudo-realistic depiction of what the charge distribution looks like in a crystal. But now I want to do it taking into account the termination. So to the left, we have the bulk. And this region is the surface region, or the end in one dimension. Okay. So as I told you before, this is not the macroscopic surface charge. In fact, it's not uniquely defined, as we argued. But if you give me some charge distribution, how do you actually compute the real thing? So there's a trick. Let me define a function, which is a function of position, which I will call rho bar. So it's the average of the charge distribution over a lattice constant. Okay? So what does this function look like plotted versus x? So this is our lattice constant. And let me start deep in the interior. So we have this window. We're doing a window average of the charge density, and now we're sliding this window towards the surface. So any guess what it looks like? Precisely. So it starts off at 0 because when you are in the interior, you have a neutral cell. So it starts off at 0, and then we get very close to the surface, you start getting stuff. this is the bulk, and this is the surface. So let me pick another, again, a cut, the initial point x0, deep in the region where this function is 0. Okay? And I can just define, and I hope you agree, okay, so we just integrate the stuff that appears because there is a surface. So, surface charge, right? And it's macroscopic. We are integrating anything, everything. Okay? And, you know, that's the meaning of this equation, essentially. So now we have one quantity that we can compute from the charge density of a finite system, and it's related to the end of this finite system. And then we have the blue quantity there that we can compute from solving a quantum mechanical eigenvalue problem, and then taking some centers far from the surface. And so this is a non-trivial statement. I'm comparing something that is related to the center of the chain to something that is at the end of the chain. And what I've claimed, what I've tried to prove, is that they are the same or almost the same. So let's check. And so this is where I introduce a model, which is basically the same model that was mentioned in the lecture of yesterday afternoon. Which is basically a 1D chain. So let me start with the simplest possible 1D chain, where you have some on-site energy and some hopping. So I'm assuming some rudimentary knowledge of tight binding. So this is the model, and so that defines the model, the Hamiltonian. We get so there is one side per cell, so we get one band. But now I want this model to be half filled, which means that I'm going to have one electron for every 2 cells. So if we diagonalize the Hamiltonian, we get a band. But because I only have one electron for every 2 sides, this band is going to be half filled, right? So this is a metal, right? So this is a 1D metal. And now what I want to do is to modify this model in 2 ways. So first, I'm going to dimerize the model so that now the on-site energies on the 2 sides alternate. And just for kicks, I will also alternate the hoppings. So I will call them T1. Actually, let me make sure I use the same convention as in my notes so that I don't get confused. And actually, yeah. Actually, I want to call this T2. So what happens? So in this case, the lattice constant was this. But of course, now the cell is doubled, which means that the Brillouin has folded. So now I have 2 bands, right? And I want to call A the length of the double cell. So this is minus pi over A. This is plus pi over A. So this is actually, the original one goes up to 2 pi over A. Now, as soon as the on-site energies are asymmetric, so they are not the same, and or the hoppings are asymmetric, you open a gap here. So you go from a metal to an insulator. Okay? So what I'm going to do, some more notation. I'm going to introduce the on-site energy asymmetry and the hopping asymmetry. So I will define E1 as some E bar plus alpha, so alpha. And E2 is E bar minus alpha. So alpha is the difference, is half the difference between the on-site energies of the alternating site. And I'll play the same trick for the hoppings. So hoppings are usually negative, so let me put a minus sign up front. And let me call T1. Okay. So alpha is the on-site asymmetry, so that's what makes white different from open from full circle. And beta is the hopping asymmetry, that's what makes the double bond different from the single bond. Okay? So, okay, we have too many parameters here. I mean, so E bar just sets the zero of the energy scale, so we can just set it to 0 from now on. This positive constant T just sets the overall energy scale, like the bandwidth, so let's just set that to 1. And so from now on, the model is completely specified by alpha and beta. Okay? So I can draw a phase diagram, I guess, in this parameter space. So we have until 45 after, right? Okay, thank you. So this is our parameter space, and let me emphasize again on-site asymmetry, hopping asymmetry. And if there is no asymmetry, that is the model that I drew first, we are sitting at the origin, and that's our metallic point, where you just had a single band because you unfold it and it's hot filled. But if you move away from that point in any direction, you have an insulator. Okay. So what I want to do is to show you some results, but it's always nice to show results versus some control parameter. Otherwise, you just have a single number. I want to show plots. So let's take a walk in this space. Let's go around circles. So that point now is the center of my loop. And I'm going to go around, and so I define an angle theta that tells me where in the loop I am. And I'm going to make plots versus theta, okay? Okay, so okay, this is a busy plot. Let's spend some time on it. So it has 3 panels. let's just focus on the first one first. So in the first panel, so the horizontal axis is theta. So that sort of tells me where on the parameter space I am. And the vertical axis is the eigenvalue. So what I'm plotting is just this energy of the eigenstates. Okay? And this is a finite chain that has 41 cells. So there is a cell in the center and 20 to the right and 20 to the left. So lots of states very closely together, right? But they are separated in two groups. So there are those below 0, those in red, those are the ones that are occupied, and those in green are the ones that are empty. So the chain as a whole is gapped, so it's an insulating chain. Okay? That's good. We like insulators to define polarization. So now let's move to the middle panel, which is very busy in itself because it has 3 curves. Okay? So let's focus first on the red, on the blue. That's the bulk polarization. So remember the prescription. I constructed this matrix after diagonalizing. I constructed this matrix here. I diagonalized it, and then I got the eigenvalues. And then the bulk polarization is just the dipole moment of a cell, the cell right in the middle, using that as a negative charge at center and an ion. Oh, something very important. I forgot to say where the ions sit. Yeah, so, and that's quite important. You cannot talk about polarization if your system is not neutral. So to completely specify the system for the purpose of this problem is not sufficient to make this kind of drawings that people usually do. There is one other completely essential piece of information, which is where the ions sit. And actually, I put it on the wrong place. I want to put it here. So there is one ion per cell. So I just chose it to sit on the same location as the field circles. So one of the orbitals of the model. So now I can compute. That's why I can compute that bulk guy. Okay? So that's the blue curve. The dashed line is this. Is the surface charge. So the blue curve was computed in the middle. The surface charge is doing this integral near the surface. And you see that there is perfect agreement. Okay? So this is a non-trivial numerical check of all the things that we discussed for 1 hour and a half. And then I plotted a third curve. That's the dotted dashed red line, which is the dipole moment of the charge density in the central cell. So that's the old textbook definition. And it sort of agrees in some places, but doesn't always agree. So that's actually interesting. So where does it agree? Why does actually, so it doesn't always work, but why does it sometimes work? And to understand that, let's look at the final panel, the bottom one, where I'm plotting the variation with theta of the intracell and intercell hoppings. What do I mean by that? Well, I've made a choice of cell. You always have to make a choice of cell to compute the bulk term. And I've chosen this one, I think. Yeah. No, I always get it wrong. Okay. Yeah. So, and on the left side, so close to pi over 2, you see that the intercell hopping is very close to 0. So in this picture, that would be this T2 here. So that's what I've drawn as the weak bond here. So when the electrons cannot hop across the boundary, actually the naive definition works. That's sort of the molecular limit. But as soon as the electrons are allowed to hop across the cell boundary, that's this region here, then the naive definition starts to fall apart, right? So I'm basically on the right side of that plot, I'm making this T2 hopping larger. Okay? So when T2 is 0, the system breaks down into disconnected units, sort of molecules. So each dimer is a molecule and it's not connected. So that's the tight binding version of localized charge. Okay? So, well, so that's that. So I think everything behaves as I've tried to argue. But let's come back to that argument in the last 10 minutes about, you may remember an argument that I mentioned about why people might think that the polarization is not a bulk property. And the argument was, shouldn't you be able to push charge away from the edge by raising the site energy at the edge, right? So we have our chain, and they have some ease, and now I change the energy at the edge. So if I raise it, I should somehow, I mean, it seems reasonable that the charge doesn't want to stay there, right? But that seems to run against everything else that we've been arguing. So nothing like trying it, right? So I'm going to make a second plot where now I'm keeping the bulk parameters fixed. So I'm sitting somewhere on this parameter space. That's not changing. And I'm going to plot the same things, but now against this delta. Okay? Okay. Topology. Something that starts to look familiar. Okay, so what's going on there? Actually, somehow the story looks better if we look at the plot from right to left. So let's start from there. So now I'm only plotting two quantities, which is the surface charge and the bulk polarization. So we have already gotten rid of the naive definition because it's no good. But so there, they agree. But then, well, the bulk polarization is perfectly constant. So the Viney functions in the middle of the chain don't care at all about raising the energy at the end. So as expected, that doesn't change. So pushing charge apparently doesn't work. So the surface charge is constant. So, but then, jump. And the jump is precisely minus 1 electron charge, so minus 1 on that scale. So polarization is shown in units of E. So can we push charge away? Yes, but only in quantized amounts. Okay? And how does that work? Well, let's look at the bands. And you see some edge states appearing. Okay? I've sort of chosen the parameter so that the edge states are visible. But as you tune the parameter, what happens, you're raising the energy of the right edge. That's the red line there. That's true. The energy of the left edge is constant because I'm not changing that. And so at some point they cross. And that's the point where the jump occurs. So what is the physical process that's taking place here? Yeah, but before that, I would call it tunneling. So, remember, red is occupied, green is empty. So the electron was on the right side, but I've raised the energy, and at some point, the energy on that of the state localized on the right edge, became higher than the energy on the left edge. So it's energetically favorable for the electron to tunnel all the way to the other end. And so we've removed. Now I'm walking in that direction. We've removed an electron from the right edge, so the polarization went up because That's the charge on the right side. So we've removed minus a minus E. Yes?
So if you keep increasing the energy of the last edge electron, you mean that it's going to all the way back to the other side?
Well, we're solving a ground state problem, right? So the prescription for solving a ground state problem is you calculate the levels and you populate them from the bottom until you run out of electrons. So, you know, let's do what you want, which is to keep the electron on the right side. So you will keep it there, but there is a lower energy state available, which is empty. So the ground state is now the electron on the other side. If you want to think about it dynamically, it's tunneling, and of course that takes a long time. So, you know, it could be a very long-lived resonance that the electron stays anyway on the other side. But as far as finding the ground state, you know, there is on this side of parameter space, the ground state has the electron on one end, and on that side, it has the electron on the other end. So, in that, yeah, does that make sense? Yeah. Right.
Actually, maybe it's more complicated. The problem is actually quite deep. I mean, it came first in the 80s in the context of the quantum project, where something similar did. So somehow, as you say, you make one state variable. I mean, you somehow push the limits.
Yeah.
If you just adiabatically push by playing with one parameter, all of a sudden one electron on the right side is a little bit above one energy. On the left side, there is a very attractive state which is empty and it wants to go there. But how does it do that? I mean, there can be a macroscopic separation. And that was actually the reason why they used in the beginning of the 80s that there must be some massively delocalized states in the sound at the same time popping up into some wormhole that allows the electron to go from one side to the other. It's really not clear how these states form. There's a whole literature of it.
Yeah, no, right, yeah. I think that's definitely true. Of course, please. Let me try to remember. Well, so maybe what's written there is wrong, and I actually tweaked the. Let me think. That's a good question. I'm confused now if what I've written there corresponds to actually what I've calculated. Yeah, actually, I don't have the answer right now. But you can certainly play with the parameters. I can give you the Python script if you want, and you can tune it. But what I did there, yeah, I'm not sure. So I should mention that all this was done with a very cute code called Python type binding. So you're allowed to look at your smartphones and Google it. It's a program that you can download to set up these type binding models, and it's very nice to play these games. So that's how this was done. Okay, last 2 minutes, sort of to water your mouth for the second half, so that hopefully you come back. Let's do another loop. Let's do this loop. So now I go back to the first slide that I showed you. Now I'm again tuning the bulk parameters, but now I'm choosing a loop like this. Okay, so that's what happens. And let's first look at the lower panel and at the blue curve. So that's the bulk polarization. Okay. So remember that's from 0 to 2 pi. Your system started at some point. It moved, but then ended up where it started. But what's going on? Because the bulk polarization is different at the end point. But the system came back to itself, so that's funny. However, it changed, but it started at minus 0.5 and it ended at plus 0.5. So it came back to itself modulo E. That's fine, because we learned before that bulk polarization is only defined modulo E. So you started in some state, you went for a walk, you came back to the same state, and the polarization changed continuously, but it came back to a different value, but that is different by E, and that's allowed by the rules that we've set out. Okay? Okay. So in terms of the Viney centers, what that means is that the Viney center started in some cell, and it actually shifted all the way to the next cell. But of course, everything is periodic, so the Viney function that was sent in at the beginning on that neighboring cell shifted to the other one, right? So this is a kind of a non-trivial loop, right? So in the first slide, the Viney centers also moved, but it was only, they went for a walk and came back to the home cell. So there was a small excursion, and they came back. So here is that they traded places, like the game of the chairs, right? So one loop is trivial and the other is non-trivial in the following sense, that in both cases, if you look at the Viney centers in the bulk, everything looks the same. That's true in both cases, but in one case, charge has flowed through the system. A macroscopic charge has flowed through the system, right? And in the other case, not. So the integrated current, if you want, is non-zero and is quantized in one case, and in the other case, it's not. So I will end there, but just to draw a cartoon, and then we go for coffee. So the picture is that these are just the Viney centers in the bulk, that in one case, they did like this. I'll call that the non-trivial. That's the one that is shown there. And these arrows are just meant to represent schematically their motion. And in the other case, they did something like that. So these two things are obviously quite different. And in one case, a net charge has passed through the bulk. And in the other case, well, it first did that, but then came back, so at the end, no charges flowed. And just, okay, one more important thing to finish. Sorry about that. I'm really pushing your patience, but I just want to say one thing, which is the surface charge did come back to itself. Because in our loop, the entire system came back to itself, including the surface. So, you know, so the surface charge, which is defined modulo nothing, has to be the same at the beginning, at the end. And so the way that happened, and that has to do with the upper panel, is that during this cycle, the charge was flowing to the left. So you were accumulating charge on the left, but then at some point, this charge that accumulated wanted to go tunnel to the right, and that restored peace in the universe because the system was able to come back to itself, keeping the surface charge and the bulk polarization always the same modulo quantum, because this was a change by one, and that happened again through tunneling or crossing of edge state. And just one sentence before your question. This has to happen. So if the cycle is such that it's pushing charge through the bulk and the system comes back to the same state, there has to be this step to allow sort of the charge to relax and come back to where it started. So this is an example of a bulk boundary correspondence. So if the cycle pumps charge through the bulk, then to compensate for the excess charge, there has to be a surface crossing to allow the system, the finite system, to come back to itself. Okay? So I'll just take a question and then, yeah.
So what happens if you do another period? What happens if you do another period? You have 4 or 5?
Well, everything repeats. Yeah. Yeah, so all these functions are periodic. Yeah. Okay, so thank you for your patience, and let's